All right, we're live. So in this video, I'm going to cover non-fixed boundary conditions or boundary conditions involving derivatives. And so let's consider again a boundary value problem. D squared y dx squared is equal to 3y squared. So we already covered the solution of this where the left boundary condition is equal to 1. But now we're going to make the right boundary condition a no-flux boundary condition. So typically this involves where you have a barrier and you can't have diffusion through the barrier, or we can do more complicated expressions, which we'll cover in a second, where we can change that boundary condition. And in your homework problem, I'll have you do one where you'll do a derivative boundary condition where you're going to have kind of a mass transfer term. So again, let's go ahead and just solve this. So we're going to let's just start with 20 points. We're going to do define our domain. So we're going to do x is equal to np linspace of -1 to 1, and we're going to do n points. And then always forget to define the delta. So x of 1 minus x of 0. And so that's going to be kind of our spacing. So we're going to define our myfun again, and we're going to pass in y. And again, we're going to set our equation equal to 0 times y to allocate it. And so we'll do our left boundary condition. We already did this before at x equals -1. And here we're going to say equation of 0 is equal to, basically we're saying y of 0 is equal to 1. And then we can do the interior for I in range of 1 to n-1. So these are interior points. We're going to set equation of I. And then we're going to do our derivative. So let me put quotes. So we're going to do y of I plus 1 minus 2 times y of I. And got an error there. And then we'll do plus y of I minus 1. And then this is all going to be divided by delta squared. All right, so this is the second derivative operator. And then we're going to say minus 3 times y of I all squared. Right, and so now we're going to do the right boundary condition. And here we're just going to use our finite differences formula. So since it's the rightmost point, we can't use the forward difference formula, but we can just use the backwards difference formula. So we just grab the last point, and I'll do this n-1, and then we can do y of n-2, right? And then this is just a derivative at the right point. And we're going to do our delta, and then we're going to just set this equal to 0. So that's going to be our right boundary condition, where we're going to have basically, this is kind of the derivative of y at the end, right, at this point. I got this wrong, so I have x of 1 here, and I really mean y of 1 here. And I probably have that typo in my previous video, so I apologize for it. So that's kind of y of -1 equals 1 and dy of 1 equals 0. And so this is going to be my right boundary condition. And then I'm going to return my equation, right? So my other equation. And then just as before, I'm just going to do sol of root.myfun. And then I'll just pick 1s as my initial condition. I set sol is equal, y is equal to sol.x. And then I can just come down here and I can plot x comma y. And we'll do this, line width equals 3, color is equal to red, and then PLT shell. And I plot this up, and I have an error here. So what am I doing wrong? Oh, I see what I'm doing. I forgot the last equation, n-1, right? Because it was overriding one of the equations. And now I have my solution. All right, so I have the left boundary condition at 1. And then if you look over here, the derivative right here is equal to 0. So it's basically a flat surface. If we wanted to flip it around, so if I wanted to come up here and actually make y of 1 equal to 1 and the derivative at equal to 0, right? So this is the equation now I want to solve. All I'm going to do is just flip this around, right? And so basically I'm going to say, now I can use a forward difference formula. So I could say y of 1 minus y of 0 divided by delta, and then that's equal to 0. And then I'm going to set here my last point, y of n-1 is equal to 1. And now I run it, And now we see this point fixed at 1 and this other condition with a boundary condition at 0. And if I want to get a more accurate solution, maybe I'll do 100 points, right? So I'll really fill this out. And again, we basically see the same solution with the 0 boundary condition. We could also play with this, right? So I could come over here and maybe say I want the boundary condition to be 2. The derivative at the left-hand side is equal to 2, right? And so if I do that, I write out the equation. And then all I'm going to do is just replace the 0 here with a 2, right? And now we kind of start seeing a different kind of solution because now we see the left boundary condition, I'm forcing the derivative to be 2. Here I'm still fixed at 1, but now I'm forcing a positive derivative. I could also flip this around and force a negative derivative. And so I could just put a positive 2 here. And let's just run this. So that would be minus 2. I run it. And then, now I have a negative derivative here. And then again, I'm forcing the solution here. So basically using this code, we can just represent derivatives just using finite differences at the boundary conditions. And basically what I think about all these equations are, these are just basically the equation at each value of x. So let me shorten this down. So like here would be x of 0. And so this is the equation associated with x of 0. Then we have all the interior points. So this would be 1 all the way up to 18, right? And so those are the interior points where the equation's operating. And then our last equation, n minus 1 is basically our x of 19. And here we're just fixing that at 1. So that kind of extends out the arguments and shows you how you can just kind of play around and put different kinds of boundary conditions in. So we can do fixed boundary conditions. We can do derivative boundary conditions. Similar ideas can be also used if you want to do periodic boundary conditions. But what the key thing is basically we can, with a couple lines of code, we can solve a boundary value problem that doesn't actually have an analytic solution, at least not that I'm aware of. I mean, it's possible that there's an analytic solution. I wouldn't even know how to derive one. But, we have just a generic structure that we can easily solve this equation numerically and get pretty accurate solutions, particularly if we kind of go out to a lot of points. See if 200 works, and we can do 200 points. And so that's going to give us a fairly accurate solution. So with that, I'll stop. As I mentioned, I had a typo in my previous equation where I had these as x's. They're supposed to be y's. I apologize about that error. Hopefully it was obvious from context. Again, if you have questions, please post them in the comment section or Piazza. And that's it. Thank you.